Hey, thank you very much. So the basic concept here is to use the Z dimension to integrate additional functionality on top of a destination die. The destination die could be a CMOS IC, it could be an interposer, but build an array of ultra-thin, separately manufactured components, which we call X chips, that could be combined from one or more different source wafers, resulting in the heterogeneous integration of multiple separately manufactured components. So the X chips are ultra thin, 1 to 20 micron in thickness, and they would be a wide variety of different circuits, RF and power transistors, gate drivers, hardware assurance chips, sensors, photonics, passive components. And then each can be made using its optimal process technology, SOI, gas, GaN, indium phosphide, etc. And the heterogeneous integration is done using advanced packaging lines, employing a massively parallel pick and place process of very large arrays of X chips. So the X chips could be produced in a standard wafer fab, front end of line, and then these large arrays are pick and placed over to a destination substrate, which could be up to 300 millimeter CMOS wafer or up to a 450 by 450 millimeter panel. So the way to create these ultra-thin X chips is first employ a material that can have and accommodate a release layer underneath. And the release layer could be different depending upon the source wafer material. So for silicon non-insulator, it's an oxide. It's an oxide under the X chips, acts as a barrier against the edge of the release layer. Or for compound semiconductors, it could be a TMH etch, or it could be a lattice-matched sacrificial layer, depending upon the type of compound semiconductor. So one of the advantages of ultra-thin is then they could be interconnected using standard thin film interconnects, such as the copper redistribution layer. So this shows a cross section of the RDL interconnecting these ultra-thin X chips. If you had a very thick chip, 30, 50, 100 microns, it's a lot more difficult to interconnect to them over the top. So the big benefits are, first, significantly improved performance, because the monolithic chip could be repartitioned, disaggregated, reintegrated, broken up into separately manufactured components, each using its optimal process technology and node. The second is with this very close vertical stacking of X chips on top of, say, a CMOS destination die, you dramatically reduce the parasitics and resulting power loss. So that reduces the power consumption. Obviously by stacking and going upstairs, you reduce the area. And then in many applications, it's all about increasing density. So you can really minimize the XY footprint as well as the Z dimension. There's actually a significant cost reduction coming from the following. First, by using the optimal process technology material, you can save money on the wafer fabrication. Second, small die have much higher yield than large die. With the etchants going between the gaps between the X chips, eliminate the big fat streets, so it can get very high utilization of expensive semiconductor material. As you'll see, that this process is very straightforward. So it's a low cost, massively parallel manufacturing process. One of the problems with heterogeneous integration is, if you wanted to put a component combining a component upstairs that has a much higher manufacturing temperature than those downstairs. Well, this constraint's eliminated because each component can be separately manufactured and then subsequently integrated. And then the resulting 3D IC has big fat copper interconnects on top. So it resembles a conventional 2D IC. So then it can fit into the downstream packaging ecosystem and use a large number of conventional packaging technologies. Another is reduced time to market. So you could have a library of destination die, a library of X chips, and then combine them, mix and match them in different configurations in advanced packaging lines to then provide low volume, high mix. And lastly, these highly integrated components really need increasingly to be tamper-proof. So there are security and sensor X chips that can then be integrated that then prevents malicious attacks. So this next slide shows examples of a number of X chips that microchip were printed, and the Accelerprint website, the resources page, lists many publications with links to these papers. And I'll get into some more details later, but with microchips printed gallium arsenide for photovoltaic solar cells, GaN HEMTs for power and RF, HBTs, a lot of work in photonics. So the company history was, Semprius was the previous company. So between like 2006 and 2013, Semprius used microchips for printing and actually took it up to pilot production. Produced millions of triple junction gallium arsenide X-chip solar cells for concentrating photovoltaics. There were very large arrays on large array panel. Each one was 600 by 600 microns, and cell efficiency was north of 40%. The cells were microchips printed to a low-cost ceramic interposer that went into a tape and reel package. Then these chip-on interposers were picked and placed on a panel. Concentrating optics put on top. Extensive reliability testing was done. A lot of on-sun performance out in the field. And unfortunately, the solar market really went downhill. And about 2013, Semprius went out of business, and Accelerprint was formed with the goal of licensing microchips for printing technology for a wide number of applications. So currently, we have two announced licensees, Osram and Sense Photonics, and a total of 6 current licensees. We have microchips for printing prototyping lines at X-FAB in Germany, Micros in Research Triangle Park, North Carolina, Tyndall in Cork, Ireland, IMEC, Teledyne Ghent, and Office of Naval Research. And X-FAB is offering the first microchips for print foundry-ready service, and these are 180 nanometer SOI wafers. And ASM Amicra is offering a high-volume microchips for printing manufacturing system. So this shows the details of the system. Is fully automatic, high volume, ISO 4 clean room class, supports up to 300 by 300 millimeter source wafers and up to 450 by 450 millimeter wafers or panels. The stamp is 50 by 50 millimeters, about a 40-second cycle time, very accurate placement, and ASM Amicra also offers an R&D system and a more precise alignment system. So you can see here the system along with the microchips for print stand. So the overview of the microchips for printing process is create a stamp. That's the stamp, more details coming, but has a custom post and spacing to match the final device design. Source wafers, which are fabricated with anchors and tethers and sacrificial layer. So this shows the anchor and the tethers and the release layer that's been chemically removed under each X chip. The transfer stamp then lifts off a large array from the source, and so that's the pickup. The pickup breaks the tethers, breaks the anchors, and the placement is then on the destination substrate. So microtransfer printing is a very simple, elegant, yet elegant, massively parallel, pick and place technology handling very large arrays of X chips. So, this example is showing 200 millimeter source wafer, but the source wafer could be anything. It could be 50, 100 millimeter, 300 millimeter. Similarly, the destination wafer here is shown as a 300 millimeter wafer, but it could also be a wide range of different destination wafers or substrates. The stamp has thousands of posts, and the posts are shown here. Each stamp picks up many die, and each die can have many X chips. So each pick and place is moving thousands, sometimes more than 10,000 X chips from the source to the destination. And depending upon the post configuration, you could, for free, spread out the X chips. So this shows an example of a first transfer picks up one out of every n X chips from the source wafer, and populates a corresponding small fraction of the destination. And then the second transfer picks up the adjacent array. So let's look at how this works with this video. So here's the source wafer, here's a stamp, it picks up an array from the first source wafer, it places it on the destination die. Here's the second stamp, then intermingles blue X chips, which are could be from a completely different wafer fab process technology, with red chip X chips, and they're different sizes, could have different spacings, etc., and they're all interconnected with a thin film interconnect. So that was the cartoon. Let's look at a video of a real microtransfer printing system. So what you're seeing up at the top is kind of the insides of the system. So there's you'll see a stamp move between source wafer, the destination wafer, and then in back there's a kind of a cleaning pad. So if there's any debris or untransferred X chips left on the post, they are removed prior to the next print cycle. So key thing is, look down here. So you'll see 3 X chips, and then here's another 3 X chips. And let's start the video. So the stamp comes down, picks up, removes the first array of X chips, puts it down on the destination die. The stamp then goes to the cleaning, make sure there's no debris on the posts. The posts are now clean, goes back to the source wafer, picks up the second array, moves it over to the destination die, populates a different area of the destination die, goes to the cleaning, any debris is removed, goes back to the source, picks up the third array, goes over to the destination, and so forth. So you can see it's a very, very straightforward process. And now let's go through this each step in a little bit more detail. So first, the destination die or substrate, and this is a close-up looking at one die, can have many options. It could be a CMOS integrated circuit, it could be an interposer, ceramic glass, silicon, plastic. It can be smooth, rough surface, planar, non-planar. It can be a wide variety of wafers or panels. So the source wafer, and again, this is also just a close-up of one die, is tightly packed with X chips. So there's very small gaps between the X chips. And the X chips are temporarily held in place by anchors and tethers, and the sacrificial layer is chemically removed depending upon different technologies, whether it's GaN, SOI, gas. So the stamp then is made out of a elastomer PDMS material. it has an array of soft posts. This PDMS material is compliant, and it's on a stiff glass substrate. So the stiff glass substrate provides very accurate placement accuracy, and the compliance in the Z dimension enables printing on rough surfaces or a variety of different surfaces. The stamp is low cost. It's made from a reusable mold. The stamp has posts where the size and spacing can match the desired X placement on the destination substrate. So the posts, the principle of operation is the stamp has this viscoelastic behavior. So the stamp's posts adhere to the X chips by a van der Waals force. And when you're picking up, you are in the fast regime. So you have the stamp adheres to a large array of X chips, picks up fast, breaks all the anchors and tethers, and you can selectively pick up a large array. And these X chips can be ultra thin, they can be fragile, just not possible to pick and place any other way. And then the stamp moves over to the destination substrate, and now you're operating in a slow printing regime. So the X chips go to the destination substrate. It has a thin adhesive, or sometimes just the van der Waals forces on the destination are sufficient. And the stamp lifts up very slowly, so then leaves the array of X chips behind. So this shows what the destination substrate would look like after, say, first transfer. So in this example, we've transferred 1 out of every 4 rows of X chips, which are shown in red. And so these are sparsely populated. For many applications, you stop there, just 1 transfer. Other applications, you may want to combine multiple material sets. So you would then have a second source wafer. Again, that could be SOI, gas, GaN, passive components, a wide variety of different materials. The stamp, typically the first chips that are transferred are thinner than subsequent ones. The stamp post design is different because in this example, the X chips are larger. So the stamp picks up every other row of X chips. So here you can see after the first pickup, every other row is missing on the source wafer. And then the stamp transfers the large array over the destination substrate, and the result is you've now combined, in this example, 3 different material systems. So let's say you have a CMOS IC downstairs as a destination die. You could have, red X chips, for example, SOI, and you could have blue X chips, gas or GaN. And then the last step is the RDL then interconnects the X chips with the destination die. So what's been proven to date is a wide range of capabilities. So we've built many prototypes, or customers have built many products using gas, SOI, GaN, and other compound semiconductors. The X chip size can be as small as 3 by 3 micron, or we build greater than 1 millimeter on the side. The etch, a wide variety of different wet and dry chemistries, field or patterned, different tether structures, dielectric and photoresist, different encapsulation technologies. So historically, the last few years, the biggest application has been in the photonics and optoelectronics area. So we have a number of customers that are building very interesting disruptive photonics products that have not quite yet been announced. Second is RF communications, particularly looking to 5G millimeter wave. A huge need for large arrays of heterogeneously integrated components. Another really important application is this bolt-on root of trust for hardware assurance. Power management is another very large market opportunity that's seeking disruptive heterogeneous integration technologies that is well served by this. And then also sensor integration. So, a very simple example here would be, and then, I provided links to different published papers. So here would be a X chip, very small, on the destination substrate. And this prototype actually used both silicon glass wafers that were 200 millimeter. And then these same X chips are readily interconnected with copper RDL. And then the bumps are formed and completes the fan-out package. And looking at the details, here would be a top view of the source wafer. So you can see a large array of X chips. And in this area, the X chips have been removed. They've already been picked up, and you can see the toes and the anchors. And here on the destination, you would have the wafer level of all the completed fan-out packages. So that's a simple example. Another example is microtransfer printing GaN X chips onto CMOS. So here would be the GaN on silicon. So GaN grown on 111 silicon. The GaN has source gate drain. This would be a top view of the GaN X chips on the source wafer. Here's the GaN X chip, ready for microtransfer printing. And then here it is on the CMOS wafer for interconnected with RDL. So in this example, you could have the GaN drivers downstairs and the power transistors upstairs. Another GaN example is this recently published paper, which shows GaN integrated onto SOI, interconnected with RDL for a single pole, single throw switch that offers a compelling competitive performance advantage. And there's a huge reduction in the vertical capacitive coupling, and that's attributed to this very tight integration of GaN and SOI, and that reduces and really provides very low insertion loss up to 30 gigahertz, as shown here with these actual measured results. And again, the papers are referenced. Another capability is, and we published this last year at a conference, is stacking multiple X chips. And these were done with very small LEDs, but you can certainly use your imagination, extend this concept to many other applications. She's done extensive work over the years, proving out the process capability and stamp lifetime. So, this paper summarizes some of the data, which is basically after 30,000 print cycles, less than 4 micron misalignment, vast majority is less than 2 micron, very high pick yield, also very high print yield. So, you could have a very simple example, as I started this off by showing just a single X chip with a fan out, or you could have very complex. And this shows some prototypes that were built that combined multiple materials. So, and each X chip has, a much different size. So combines a 270 by 70 micron silicon IC with GaAs and GaN X chips. So, this could be very important for photonic integrated components. So where one would be highly desirable to heterogeneously integrate a large number of different components, lasers, modulators, drivers, detectors. Each needs to have very precise alignment, for the fiber coupling. Use the best technology with high wafer utilization to really minimize the design size and minimize cost. So we've actually published a number of papers on a wide variety of different photonics structures. So the idea here with the hardware security is to enable very secure ICs. The source wafer, producing the destination die, could be produced in ICs, IC wafer fabs anywhere in the world. Use state-of-the-art advanced CMOS nodes from Taiwan, as an example. But then sensors and security X chips are then stacked on top and interconnected with RDL. So basically, the security and sensor chiplets are then embedded in the interconnect of the destination die. And this could really enable a wide variety of different anti-tampering capabilities. So another big market need is to improve the density and efficiency of power management devices. And power management devices are by nature very heterogeneous because today you have controllers and drivers built in a CMOS process technology. You have a different process technology to build the power transistors. You have a different power technology to build capacitors. You have a different technology to build inductors. You really want to tightly integrate all these different components and minimize the parasitics, so you could then go to very high switching frequency to then shrink the size of the passive components. And this microtransfer printing gives a lot of flexibility and many design options to do that, because you could then, one option would be downstairs on the monolithic, use best of breed technology for a given application. GaN, gas, silicon, whatever. But then rather than putting the gate drivers off chip, which adds parasitics, or trying to monolithically integrate them, which adds a whole lot of cost and complexity and also integrates parasitics, just use X chips that are then stacked on top. So now you have an X chip for each. You have basically a large array of microconverters, each with its dedicated driver and power transistor. Or another approach could be downstairs on the CMOS die, do what has been done for decades, monolithically integrate gate drivers, controller, protection, monitoring, and then upstairs use power transistor X chips. So the benefits, whichever option you pursue, the benefits are really minimizing the parasitics, so you can go to very high switching frequency and then achieve all the benefits resulting from that, which is very high density, very fast transit response, high efficiency because of lower switching loss. And then this enables multi-stage hybrid topologies. So you could have, once you have a large number of switch and driver pairs, this really opens up and makes practical a number of topologies that are just not possible if you're using a bunch of discrete, separately manufactured components. And then products can then fit into the downstream package and test ecosystem because the resulting Power 3D IC resembles a 2D IC. So kind of schematically, this shows basically the value of disaggregation. So the conventional half-bridge circuit would have gate drivers. Say for a buck converter, there would be an upper and a lower power transistor with a gate driver, inductor, capacitors. But if these are separately manufactured components and they're separately located, the parasitics result in a lot of loss that forces you to have low switching frequency. But if you would then disaggregate and break up each of these power transistors into n number of upper power transistors, n number of lower power transistors, each tightly coupled with a corresponding n number of gate drivers, now you get ultra fast turn on and turn off time, very minimum parasitics, and that's it's got like a performance advantage of disaggregation, reintegration, by heterogeneous 3D stacking. Okay, so I think in 5 minutes, under my allocated 45-minute time, so I think I have plenty of time for questions.
Thank you so much for the presentation. I think Dr. Raj have a question. So Dr. Raj, would you like to ask yourself? So maybe I can read it. So are chips always facing up while being picked? Oh, Dr. Raj?
Yeah, I think my question is the transfer always done with the chips facing up? And if they are facing up, then I think you will be doing lithography to form these interconnects. So it must be a very non-planar surface. So I want to know what kind of, are you still using this liquid photoresist? So is it essentially a wafer scale process, or can it also be done on a panel scale?
Yeah, it can be both wafer scale and panel scale. The chips, when they're picked and placed, they're generally active side up. There are ways of doing a flip chip and making active side down, but the vast majority of what we've done is active side up. And the big advantage is, since these chips are so thin and the gaps for the etchant in between the X chips serve as double duty, because that gap space can be used for the thin film interconnects. So the feature size, we're not pushing the limit in the thin film interconnect technology. These are typically, well north of 10 micron lines and spaces, and the RDL can be, 5-10 microns thick, and the surface does not need to be that planar. There's some applications where the destination substrate has holes, so the X chips can be put in a hole and then interconnected. It gets a lot more problematic, as you know, when the chips face up are thicker. But we're not going there. We're focusing on ultra thin.
Thank you so much. So is there any other questions?
We have a couple of questions on the chat.
Hi, Bob. My name is Rajesh. Thank you for the talk. One quick question is, when we stack these dies, how strong are the van der Waals forces to hold them together? Particularly, I'm more interested about sort of the thermal and mechanical stability of the stack.
So I would say that the vast majority of applications use a very thin adhesive. So that adhesive can then accommodate very rough surface destination. That adhesive then holds the X chips in place, particularly if you then interconnect them with an RDL, they're really held in place. Some applications, and the adhesive is, I can't remember exactly how thin, but it's really thin. So there's not that much thermal resistance. but a lot of these applications, this goes into a flip chip, so the heat comes out the top side anyhow. So for example, the gas applications doesn't have backside cooling, it's all, active side cooling. Other applications do have van der Waals forces that temporarily hold, so they would adhere the X chips to the substrate. In this case, the substrate needs to be a lot smoother. I don't know off the top of my head have any figure of merit data on how strong these van der Waals forces are, unfortunately.
Yeah, thank you for clarifying. I think you answered most of my questions.
Hi, my name is Mojgan. So you mentioned the benefit of microtransfer print in terms of reducing the cost, in general. So I'm just wondering, what's the add-on cost of the microtransfer print itself? I mean, you described the stamp search basically relatively cheap, but just wondering how basically the cost of microtransfer print in high volume or relatively lower volume it can be included.
Well, that's a great question that unfortunately can be answered by it depends. So, the system itself is like a pick and place system on steroids, upfitted with microtransfer printing stamp. You can, these pick and place systems are pretty inexpensive compared to wafer fab equipment. We've got a pretty fast cycle time, so one system can handle a couple 300 millimeter substrates an hour throughput, and that's really fast compared to other pick and place. So that's actually the cost of transferring. So now you say, okay, well, you've got to add a release layer, you've got a couple of additional processes added to the source wafer. Okay, so maybe that's, a couple mass steps. But then that cost can be offset by you're eliminating those big fat streets between each X chip, and you wind up with small gaps between the X chips. So the cost is a big factor of how tightly you can pack the X chips on the source wafer, and then what's the source wafer utilization. And so you'll say, well, what about all these X chips at the edges? Well, this stamp can pick up X chips going off the edges. So for example, the stamp can go pick up the X chips here. Granted, the stamp utilization is low in this area, but it can move the X chips here from the source over here on the destination. So you can get high source wafer and high destination wafer utilization depending upon the application, depending upon your stamp design, etc. But then a really big cost in semiconductor manufacturing is yield. And by having a large array of very small X chips, the yield can be higher, particularly if there's some clever design on fault tolerance. So those are the major knobs affecting cost, which is why I can't give a definitive, here's the % cost reduction, because it varies so much depending upon the application, depending upon the specific design.
I understand. Thanks a lot. That was very helpful. And the second question I had, so you talk about the, some of the sizes of the source versus destination. Just wondering if there's any requirements on the minimum size on the destination as well as the surface roughness. Is there any requirement there that needs to be met?
So actually, yeah, I mean, have a very wide design space. I think where the boundaries are is kind of a grayscale. So again, it's also hard for me to provide definitive numbers. I can provide a lot of anecdotal evidence, however. So for example, what Semprius did, the ceramic wafer was 150 millimeters. It was, I think it cost like $4 or $5. It was a really, really cheap interposer. I can't remember the surface roughness, but I think it was, north of 100 microns. So it was a really rough surface. And microtransfer printing to it was just fine because we put down that adhesive layer that accommodated that surface. In terms of the X chip size, I would say, one sweet spot has been, in the 600 by 600 micron range. There's been some X chips that I mean, as you can see here, really small, 3 by 10 microns. Another advantage is, these X chips could have very rectangular aspect ratios.
How about destination? Well, actually the X chips are really small, but how about the destination? Because you're printing on those. Is there any minimum requirement size on the destination?
No, again, the destination could be a wide variety of substrates. I've done, certainly a lot of work on ceramic interposers, printing on CMOS, a lot of work on large area glass. The placement accuracy is typically plus or minus 1.5 micron. So if you had monolithically integrated ICs on the destination, if you're interconnecting them with north of 10 micron RDL, you have a lot of, you have some margin. This wouldn't be a appropriate technology. So yeah, I think each one of these heterogeneous integration technologies serve different applications. So, I think hybrid bonding is really good for stacking, memory on logic, or CMOS image sensors, or chip on chip, where there's a huge number of fine geometry interconnects. I think microtransfer printing is much better served for different heterogeneous integration materials and ICs that typically have lower I/O count. So, they have very relaxed interconnects, and a couple micron placement accuracy is just fine. So that's why the destination die or substrate requirements are pretty loose because of the nature of the applications.
Thank you. That was very helpful.
So is there any other questions?
Yeah, I can ask one, mostly for students, on basically your business model. Is it a tool? Your business model is based on selling tools, or doing contract R&D with selling tools, or what is the main revenue path you are seeing?
Yeah, I mean, that's a great question. It is really licensing, and you can kind of think of us as, like, hopefully the Rambus of, microtransfer printing. And the reason for that is, and I used to work for, Applied Materials, back in the day, and selling semiconductor manufacturing equipment, whether it's to wafer fab or to packaging, it requires a worldwide footprint of service and support. Customers want 24/7, service, spare parts, etc. So they really want the big equipment manufacturers to be providing the tools, the service, and support for those tools. So, we are partnering with the industry leader, ASM Amicra, offering these microtransfer printing systems. So, our business model then is to transfer the microtransfer printing technology, and Accelerprint has over 500 patents. So we get a small royalty on product sales. We also do a technology transfer. So we have our engineers. Half of our company is at Micros, which is has a 200 millimeter wafer fab in Research Triangle Park, and the other half of our company is at Tyndall, that also has wafer fab and advanced assembly line in Ireland. So we then support via project funding customers in evaluating the technology, developing prototypes. We can really help customers go down the learning curve before they make an investment in buying a microtransfer printing system and moving it in their own advanced packaging line.
I have a question.
Yeah, go ahead.
Okay, thank you. The gallium arsenide chip for solar cell, how much is it for high power, high voltage applications?
Well, what Semprius is doing, this is concentrated photovoltaics. So the optics would concentrate, I think it's up to 1,500 suns. So very high concentration, tremendous amount of solar energy concentrated into this very small cell. And you can see the interconnects on the top. The heat dissipation was not much because the cells were so small. They're spread out and we have so many of them. The output voltage, as I recall, was typical of a gas triple junction cell. It was more, I think, like the 2.5 volt range. So it was not high voltage per cell, but then we had thousands of cells on a panel, and typically we would put these cells in different parallel series configurations, depending upon what the module manufacturer wanted, because oftentimes it was desirable to have higher voltage out. I think it's on the order of 50 volts coming out of each module. And then there were many modules on a tracker. So the output voltage of, say, 10 kilowatt tracker would certainly be high voltage to going into the inverter. But that was because there were thousands of 2.5 volt cells combined.
And one more thing. Is gallium oxide also have the properties that could be used for smart materials like high voltage, high energy applications?
I'm sorry, you're asking, is gallium arsenide?
No,
suitable?
not arsenide, oxide. Do you have, can you give me a little bit, if you know about gallium oxide?
Yeah, I read a little, and it looks, like exciting new material system.
Yeah, it's a new material. Yeah, it's a very promising material. I have came to know about, and it has some applications in relation with high voltage and high current, which is interesting because there are very few materials that are in those range and can actually have significant impact on, just like the solar world we have right now.
Right. Yeah, so I see huge. I think clearly the way forward is new materials, and gallium oxide is a great example. I'm showing my age here, but the problem with gallium arsenide, it was gallium arsenide blows away silicon in, all of the performance attributes, except one. You cannot build complementary devices. So
Correct.
it was not
It has a
good.
non-uniform band gap.
Yeah, so it really got relegated to more niche applications, where I think with heterogeneous integration, you can kind of change that equation, because now you don't need the new material to do everything. You can use the new material to do what it's really best at. So you could have, for example, the new material downstairs, and then if you need some low voltage control or driver circuit or whatever, you could complement that new material by putting X chips, completely different process technology, maybe a very conventional process technology like SOI upstairs, and then get the best of both worlds.